Welcome back to another exciting piece of information regarding electrostatics. This is kind of the second of the three AKS we're supposed to cover for this unit and this test. And so this is going to be about Coulomb's law, and we got to compare that with gravity. I know gravity was last semester, but it's back. And so one of the things we're going to be doing is comparing these two forces with one another because Coulomb's law deals with electrostatics or electromagnetic force. Gravity obviously doesn't, but we're going to compare the two. So that's kind of the ride we're going to be on here. We got a few questions to answer. One is what affects the amount of electrostatic force between the two objects, or two particles is probably a better way to have written it. What is Coulomb's law? That would be a good one to know. And how is Coulomb's law similar to gravitational force and the universal gravitational law formula that we used back in the fall? Really, Coulomb's law is about the only vocabulary that we haven't introduced. So let's go through these three things with no further ado. To begin with, we've talked a lot about forces first semester. Force was any kind of push or pull, but when we really get down to it in the universe, they're considered to be four forces, like four fundamental forces that exist without necessarily us having to push or pull on something. Two of these involve the atom. There's forces that hold protons and neutrons together. There's forces that involve protons turning into neutrons and decay and those types of things. So we're not discussing those. The strong force, as you might imagine, is pretty strong. These forces, particularly the strong force, is way stronger than gravity and way stronger than the electromagnetic force. So gravitational force we went over back in the fall. Again, this was just an attraction between any two objects that have mass and energy. It's wanting to pull them together. And even though we experience gravity around us, gravity in comparing to these four forces is actually the weakest of the four. And the electromagnetic force is what we're getting into now. This is an attraction or repulsion, but it doesn't have to do with masses. It has to do with the charges, the positive, negative charges that particles might have. All right, so let's go specifically to the electrostatic force, and we're not really discussing the magnetic part of this yet, so I'm just going to call it electrostatic because that's consistent with what we've been talking for the past week. And what we're looking for in this is what's going to affect the electrostatic force is the charge of the two particles. Again, so we're looking at how much of a push or a pull is there between two charged particles. So what we're going to be looking at is what is the charge of the two particles, right? If they don't have a charge, then there would not be a force on them. So there has to be some kind of a charge. And then the other thing that's going to affect them is the distance between the two particles. Fundamentally, these are the two factors that will determine how much actual force there is, how much pull or push there is between the two particles. We worked on a PhET simulation where I wanted to give y'all an introduction to looking at these two variables. And in the PhET simulation, we manipulated a couple of things. We had two charges that were illustrated, and we were able to change the charge anywhere from positive 10 to negative 10, and the same thing with both of them. And we had a resulting force up here at the top, and we could also change the distances. So one of the things I asked you to do was just to leave the charges constant and change the distance. And hopefully you made a graph that looks something like this, because as the distance increases, the amount of force is going to go down, down, down. That should make sense with the lab activities that we did in class. Again, as we moved that charged wand closer to a Coke can, we had to get it close for it to be able to start to attract it. The same thing with that water stream. If we held it far apart, very little force was there. And so it makes a nice little curve like this, and we'll get to the mathematics here shortly. And on the other side is if we increase the charge of one of the particles, so hopefully in your lab activity, when you did this, you just changed one of these from 1 to 2 to 3 to 4 to 5. And when you graphed it out, it made a nice straight line. So the idea with this one is that as we increase the charge, we get more and more and more and more and more charge, we get more and more and more and more force. Kind of makes, again, I kind of like it when the science seems to make common sense, and both of these do. So again, the farther apart things are, the less the force is, the stronger the charge, or the greater the charge, the stronger the force is going to be. The one thing that was a little bit different for this, and if you can quickly look at this and see the difference, the only difference I made here between the left picture and the right picture was in the left picture, the charge 2 is 5, and in the second picture, charge 2 is -5. So I flipped one of them around to be negative. So in the left-hand picture, both charges are positive, and what you see in the picture is that you have arrows pointing apart from each other. And again, this should be talked about that when we have like charges, like positive, positive, the force is going to push them apart. On the right-hand picture, when we have opposite charges, we have a +5 and -5. Notice the arrows flip around the other direction. It's not that only one of them flips, they both end up flipping. So if we have similar charges, they're going to push apart. If we have opposite charges, they're going to push each other together or pull together. Right. So Coulomb's law is mathematical. It looks like this picture that's here on the left. Again, it looks a little confusing, but it's really not. So the big F stands for force. There's a couple of Q's in here that are the charges, like we just saw in the PhET simulation picture. And then we have an R for radius. Again, that's going to be our distance of separation. K is in here. That's a constant. So there's a number that we plug in there all the time. Again, that's what constant means, and it depends on the materials that we're using. But we don't have to worry about that too much because, fortunately, we don't really need to do any calculations with this. What we end up needing to do is we want to say, given some situations, what happens to the force if we do some things with the charges or if we do some things with the distance. We did stuff similar to this first semester with gravity. You know, what happens to the amount of gravity if a planet got bigger? What happens to the gravity if the distance gets bigger? And that's kind of what we're going to be doing here. If you remember back to when we did this first semester, we used ones to be able to make comparisons with our math because it made everything easy. I'm going to work out a couple of examples showing how to do that. So here's a Coulomb's law example question, and it says, if the magnitude of the charge of each of two positive charge objects is halved, what's going to happen to the magnitude of the the magnitude of the force on the object? So here's what we're looking at. If the magnitude, again, that means amount of each of the two positively charged objects is cut in half. So when we used ones in the fall, again, we took a formula like this and we just plugged in a 1 for everything. So we plug in a 1 for K, we could plug in a 1 for Q, we could plug in a 1 for the other Q, and we could plug in a 1 for the radius. So if we did all that together, our answer would be 1. Right? Because we don't know in the question what the force is. We're only trying to compare, what would it change to and by how much? So in the question, it's telling us if we take the positively charged objects and cut them in half. In other words, if we take each of these and cut them in half. So I'm going to take those ones and replace them with what the problem tells me to do, is to make them half as big. The radius doesn't change and the constant doesn't change. And if I simplify everything, like multiplying by 1 doesn't really do anything, dividing by 1, well, 1 squared is 1, so dividing by 1 squared doesn't do anything. And so 1/2 times 1/2 gives me my answer, and 1/2 times 1/2 is 1/4. What that tells me is that if I cut the charge in half on each one of them, the overall charge is only going to be 1/4 as big, or excuse me, the overall force is going to only be 1/4 as big. So if I cut the charges in half, the force is going to go down by 1/4. Okay. Again, we don't know what that original force was, but if we did know what it was, then that's what our answer would be. All right, erase this. All right. It's been a while since I have used the drawing tools on here. Another problem that we have on here. The diagram below shows a pair of charged spheres and the separation distance between them. Compare the charge between A and B and between C and D. All right, so what we're doing is again on this one is we're making a comparison. We could do the math because we have a charge, we have a charge, we have a distance, we have a charge, we have a charge, and we have a distance. But in this one, all this asking us to do, and I took this from a multiple choice problem that might be in your Edge Elastic, where you've got multiple choice possibilities to say which one is several times bigger than the other one, or which one is several times less than the other. So what we can do is, again, use our one, say, let's pretend that the left-hand side is our 1. So instead of plugging these numbers into the formula, I'm going to let this be my basis of comparison. And again, take my formula and plug ones in for everything. So 1 for K, 1 for Q, 1 for Q, 1 for R squared. If I do all that, then I've got a 1. All right, so hopefully you're following along with me here. Now, if I'm comparing these two, what did my charge change to? Well, this was 2 times 10 to the negative 6. This is 4 times 10 to the negative 6. That's twice as big. So the charge on C is twice the charge of A. So instead of having a 1, now I'm going to have a 2. Same thing over here. Charge B was 2, but charge D is 4. That's twice as big. The constant's not going to change. I really don't even have to write it because multiplying by 1 doesn't change anything. And then on the bottom, the distance was originally 3, and now it's 6. Again, that's twice as big. Now, the key here is, as we make a comparison, we don't want to say, well, that 6 is 3 bigger than 3. We want to say that 6 is twice as big as 3. And so we want to use multiplication and division things here. The bottom part of the fraction is supposed to be squared. All right, so if I do this and do the multiplication, 2 times 2 is 4. 2 squared is also 4, and 4 divided by 4 is 1. And the math shows me that my answer in this one would end up being exactly the same as my answer on this one. So the overall force between the particles in these two diagrams would end up being the same, even though they have different charges. So increasing the charge should make it go up, but increasing the distance is going to make it go down. And basically those two things cancel each other out. So the force on these, the force on this one would be the same as the force on this one. Again, we don't need to figure out what that force is. We're just going to be able to say that they're going to be the same force. Okay. If we go back and we want to compare, this is the third part, compare Coulomb's law with universal gravitation. So over here on the bottom right, this was our formula from first semester, which was the universal gravitation formula. And if you kind of glance at them, you'll see that they're in the same format and how they're laid out. So they are very similar. They both have an r squared on the bottom, which means that that's going to be inversely proportional to the distance between them. So whether it's gravity or whether it's the charged particles, the distance is an inverse proportional. In other words, as the distance gets bigger, the amount of force is going to go down. It's also a squared inverse, so technically it's an inverse square relationship, which is why earlier we saw a curved graph on it. The top part, the Q's get multiplied together over here on the left, the M's get multiplied together over here on the right, so they're directly proportional. So as Q gets bigger, F gets bigger. And on the right-hand side, as M gets bigger, F gets bigger. And we saw that in the graph, and that's why it makes a straight line up graph. All right. Each of them has a constant. The left-hand formula has the K, and the other one has a G. Now, those constants are different. I'll go over that in a second. But these are the differences. Gravity is always an attractive force, always pulling things together, whereas the electrostatic force can be a repulsion force. So it can attract, can repel. So that's one difference that's there. Another big difference is that the G constant is a way smaller number than the K constant. And what that ends up doing is it gives us a smaller answer if we plug things in. And the reason for this is that gravity is a weaker force than the electrostatic force. Seems like gravity is strong, not really. Just this the one we notice all the time. All right. And then the last thing, the obvious difference, these Q's stand for charges. So the Coulomb's law uses charges, and this other one uses M's for mass. But the way that they're laid out, the way that you do the math with them is essentially the same. All right. So again, in summary, what's going to affect the amount of electrostatic force is the charges that we have on each one and how far apart they are. That's it. What is Coulomb's law? That we have a formula for that. That's on our formula sheet that we can always refer back to. The charges are on top of the formula. We multiply them together. The distance is on the bottom, which gets squared. Those two things have a constant that we multiply them by, and that ends up giving us the amount of force. And hopefully we just saw the layout of them is very similar. The only difference is they have a different constant. And Coulomb's law deals with charges, whereas the gravitational force deals with masses. So thanks for sharing your time with me. Go ahead and stop this and take care.